Good morning. Welcome to our first press conference of the day. This one is Looking Under the Ice, Initial Findings of the Nereid Under Ice Vehicle. And we'll have three speakers, and they will be speaking in this order. Christopher German, he's the project co-principal investigator at Woods Hole Oceanographic Institution in Woods Hole, Massachusetts. Michael Jakuba, he's lead project engineer at Woods Hole also. And Antje Boetius, she's chief scientist with the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research in Germany.
Good morning, everybody. It's a great privilege to be here today speaking on behalf of our team about this new vehicle that we've designed and developed over the last few years. And what we're bringing together here is a hybrid of bringing together of actually two things that have been going on. First, the project to design and build the ROV, and then secondly, our opportunity that we had with Professor Boetius earlier this year to actually take the ROV out to sea in the Arctic and give it its first testings. There are many reasons you might want to build an ROV that could operate under ice in the oceans. And you're going to hear about 2 or 3 different long-term plans we have for use of this vehicle. But a first starting one that I think everyone can relate to easily, since it's 8 o'clock in the morning and I don't want to tax you too hard, is the case of the retreating and thinning Arctic sea ice. So we have a slide here. Don't have a pointer. Thank you. I did have a pointer. So there are 2 things to be showing here. One is a plan view of retreating sea ice compared to recent averages, and then the second one over here is actually showing the monthly variations in Arctic sea ice cover, and the red arrows here just show the time when we were there this year. As you can see, at the time we were there, you couldn't tell that we weren't heading for another record low. It turned out things weren't actually that bad this year. But there's still this long-term trend that we know that Arctic ice is not only retreating, but it's thinning in the process as well. The Arctic ice that is still there isn't necessarily as thick as it used to be. And so that's been a particular attention that we, or a particular issue we were able to pay some attention to this year with our first dives, that not only were we able to achieve the first engineering dives, but also to achieve some important scientific goals as well and demonstrate the scientific capabilities of the vehicle. In terms of the thinning sea ice, one particular question we wanted to address was building on some work you may already be familiar with that was reported in Science about 18 months ago from Arrigo et al., where what they'd noticed was that if you actually took transects into the Arctic from open water to where there was ice cover, what they found was that there was high evidence of high concentrations of organic matter underneath the ice. Now, if you only measured the organic carbon content alone, you wouldn't necessarily know whether that was living material or just material that had been swept under there and been harbored there. But what they were able to do at the same time was to measure the dissolved nitrate concentrations, a nutrient that's essential for life, and they were able to show that there was a depletion of dissolved nitrate in the same locations where there was this high buildup of organic carbon. And so this led to this hypothesis or conclusion that there must be life happening underneath this ice. And the question became, well, how is that going to respond as the ice thins? Apparently there must be enough light penetration through the ice that can drive photosynthesis. So what might look on the surface like a barren wasteland may actually be a thriving biological ecosystem. So I'm going to let you in on a secret. Not everything in this photograph is an unperturbed ecosystem. You can see here the wedge of the icebreaker working its way into the ice, and if you look carefully you can see many shades of blues and whites in the sea, but in fact in some of the places where the ice has been disturbed you can see greeny-brown discolorations. And that's what actually we're talking about. This is the algae, which are the base of the food chain underneath the ice. These are photosynthetic algae drawing enough light from the underside of the ice. And the way the data was collected in the past program I showed you was by actually driving an icebreaker in, breaking up the ice in a way like this, then collecting the water samples, then making the measurements and coming up with the conclusions they had. We figured there's probably a lot more to the story than just that, but to really get into a more subtle and more sophisticated complexity of the program, what we really needed was to actually have a vehicle that could actually penetrate or disappear off underneath this ice to go and study the unperturbed system without having to drive the icebreaker into the ecosystem and perturb it along the way. And that's very easy to say, which is why I get to say that. How you actually solve that problem is a much more tricky thing. So this is where I step aside, and I'm going to hand it over now to Mike Jakuba, who was the lead engineer on the program, to explain exactly what they did and how they made it work.
Thanks, Chris. Well, the key piece of technology was developed for the Nereus deep diving robotic vehicle, which you can see on the right of the screen here. And it is this fiber optic tether that links the vehicle to the operators and scientists aboard the ship. And since it's probably pretty difficult to see from where you are, I've asked for a few samples to be passed out so you get a sense of just how thin this stuff is. The system itself consists of 2 spools of this cable, which are wound into 20-kilometer coffee can-sized canisters, one each in the depressor and another in the tow body. The depressor and the tow body go over the side of the ship mated to protect the fiber as it goes into the water, and then separate at a safe depth, after which the tether provides just a communications-only link to the vehicle subsea and not providing power like a traditional ROV. In the case of NUI, instead of using this to allow us to go very, very deep, we repurposed it to allow us to move over extreme horizontal distances from our host ship, and therefore get away from the influence of the icebreaker and solve the problem that Chris was mentioning. Of course, there are a lot of other things about working underneath the ice. In particular, we have the vehicles designed to be robust to loss of this tether, since unlike a more traditional ROV that would consist of a oceanographic cable like this combined with an umbilical system, you can't just haul back on this to bring the vehicle back home. So the system has a number of all the critical systems or systems that are based on past experience prone to failure are at least doubly redundant, as well as we have a number of emergency beacons and other communication aids to help us operate the vehicle in the event that the fiber does break. And we also rely critically on the onboard autonomy in the vehicle to help us guide the vehicle back home, and so that we know what it's doing when and if the fiber does break. Now, of course, we also focused on building a vehicle that was specifically for exploring the underside of the ice and for exploring the sea floor underneath the ice. So that what we were after is effectively a traditional remotely operated vehicle that might work on the sea floor, but inverted. So the vehicle has the ability to hold station relative to the ice, to land on the underside of the ice, and contains a large payload bay between the 2 landing skids on the top here that holds space for upward-looking instrumentation, as well as a large main payload bay, including the main HD video camera, to hold instrumentation that can be used either to look up or down, as well as forward. In this case, you can see it populated with a series of fluorometers that we had on this particular cruise this summer. One of the major challenges that we had to face in working in the Arctic was to navigate the vehicle and operate underneath the large ice floes when everything is moving and rotating. And to give you a sense of what that looks like, this is ice radar from the ship's navigation radar. And so you can get a sense of, and this is over the course of about 4 hours on our last dive, and you can get a sense of how dynamic the situation is. This is the flow here that we were working underneath for our last dive. This is another dive track to give you a sense of the scale. And of course, this raises the question of exactly what happens when the fiber does break, because it's not particularly hard to do that. And so, in fact, it broke on our very first dive. And fortunately, the onboard autonomy worked as designed. The vehicle immediately dove to a safe depth. The vehicle was rather close to the ship at the time, and the ship was using its thrusters all the time. So that part of it worked, and then it waited patiently for us to establish communications with it over the acoustics. Then we were able to guide it back into a recovery hole that was maintained by the ship. You can kind of see it here. And bring the vehicle back up to the surface after it had reported to us that it was in open water. So I've talked about the sea ice concept of operations and about moving far away from the vessel into relatively undisturbed water, but we've designed NUI or NUI to work under ice in a variety of environments and in a variety of different modalities. So one is working on the sea floor in ice-covered seas, whereas a traditional ROV is constrained by a system like this to stay more or less underneath the ship, and the ship is constrained to move within the ice. That gives a traditional ROV a very limited amount of time to work in a given location. NUI can swim to a portion on the seafloor and wait there for as long as the fiber optic tether allows, as it pays out of the canisters in the depressor and on the vehicle. And ultimately, we'll take NUI underneath glacial ice tongues and shelves. For initial trials, working underneath the sea ice was definitely the right call, but NUI was designed to work underneath the glacial ice, where there isn't the possibility of rescuing the vehicle if something goes wrong. So we'll rely even more on the autonomy and the redundancy that I spoke about. And now, whereas there are certainly a number of autonomous platforms that have been used to fly underneath in a variety of ice-covered environments, including the glacial cavities, what NUI provides as a complementary capability is the ability to use the real-time video and other sensor feedbacks that are coming back all the time to enable scientists to effectively explore in real time and to react to the unexpected. Let's head on to Antibelgius.
So the greatest fun in science is, of course, when people tell you you can't do that, or you won't manage, or this is not possible, and then you go and do it anyway. And so that was the situation with our expedition. I planned it in 2009, and at this time I had the idea of doing a couple of things at one time, namely finding out how climate change changes the under ice habitat, and secondly also to explore the deep sea at the same time. And in 2009 I contacted various institutes, so IFREMER, our own German institutions, Woods Hole and others, to ask, will you have a robot ready 5 years from now that can help us doing this kind of exploration? And this robot didn't exist at that time, but knowing Chris and Andy and others involved, I had big hopes, and I wrote it into the cruise proposal anyway, that this robot would exist 5 years later. And so it was a fantastic joy to be able to work it. And so I have to backwards. So I think the next is, so why are we so fascinated with these under ice situations? There are several reasons. One is it's really a habitat for life, and it has always been a habitat for life because Earth has always been a planet with an ice cover. Sometimes a very big ice cover, sometimes less so. And recently, you all know that we are losing the cryosphere, and the hardest answer of them all is, what will it mean to us? What will it mean to life on Earth? So when you start on the scale of simply such a flow of ice, it's hard. It's like a bottom turned up. Of course, icebreakers can steam through, but with the results that Chris has pointed out to you. And from new small investigations that we had, we knew that basically the underside of ice is a focus area for animals to feed on ice algae, algae that grow in and under the ice. Now, the other big question is, when we think of the ice flow as it melts in summertime, it forms these so-called melt ponds on top of the ice. These are freshwater ponds. And when you think about ice, it's not see-through really, but when it melts through, then light can actually penetrate to these melt ponds and also change the irradiance under the ice, with the consequence that melting goes much faster. You have these hard ridges that can be really obstacles to ships going through. So if ice flows collide and these ridges build up, you can have some 8-meter ridges, though the rest of the ice is just 1 meter, and that's where the ships can't go through. So all of these questions, what is the future of ice? How does it behave when it melts, when it gets thinner? All of these need some undisturbed observations with various sensors. And that was the main purpose of building that robot. Now, the biggest problem, as you know, is navigation when you don't have GPS. So we have many problems that have to do with this. And so, of course, when the robot came together, our big question was, will it be able to navigate, especially when we lose the fiber cable contact? And of course, I was also asked by the captain when we started out, so who will pay for losing the robot? Because the captain was not at all convinced that we could handle that. So here you see one of the first sensor suites that we had obtained from having the robot in. And so you have to imagine that on the one hand, physical data, they allow us to understand the environment for organisms. And what you see here is on the left side, you see light transmittance, so sunlight shining through ice. And you see, for example, exactly that. So we're moving through ice, and then when there is a melt pond or when there is an open leak, then the light can penetrate much deeper. But you can also see that light penetration is really limited, and so organisms that need light, like photosynthetic life, they have to accumulate in such areas. You can also see, simply by looking at temperature or salinity, that the melting of ice causes a freshening of the surface layer of water in the Arctic Ocean, and this causes stratification because density changes, and fresh water floats on top of salty water. And in fact, in this, some of the first profiles of this undisturbed habitat show you that you have several zones that are usually not mixing, like this top 2-meter zone, and then one that is at about 10 to 20 meter, and then one deeper one that is mixed in wintertime. Now, organisms accumulate at such density zones, and you can see that here chlorophyll measures the fluorescence of algae, and you can see there is a big peak right exactly in this 2-meter zone, and so this one you cannot measure with an icebreaker moving through. You can also not measure with any other kind of equipment like profilers we put on buoys, because they will not go up to the top 2 meters. They have to stay put because of the ridges and the icebergs. So all of our buoys that we have anchored in the Arctic, in the ice, they don't give us the surface resolution. So to our knowledge, when we went out, there was no other tool on Earth who could do this kind of measurements for us. But that's only one part of the story. When you have these physical chemical data, you can start making sense, but humans have eyes and they behave according to vision, and so when we see things, we can understand much better. What you see here are stills, are photographs, photographed against the underside of the ice floe. So just imagine you're looking up now, and then you see these thick accumulations of algae. This brownish-greenish mass are ice algae that are adapted to growing in such little ponds under the ice, and they can form gigantic masses of biomass. And these we have completely overlooked. In fact, Nansen, when he was out in his first expedition some more than 100 years ago, he described some of these algae, and we have never been able to map them really, so they were always a myth to us. How much biomass can really be produced under the ice? Can this explain why we have so much life in the Arctic Ocean that is otherwise highly oligotrophic? In fact, when you go to some of the published data, I even heard talks here, where people still assume that under the ice there is zero production, and that is utterly wrong. And we have to include that when we want to understand carbon cycle in the ice. Now, let's take a dive with Nui. And here you see the picture from Polarstern, our icebreaker, when we launched it. We filmed the operations to also document how robot can be operated from the ice, and now we're diving under this ice landscape. And here you see why we cannot simply send some gliders or can simply send some other types of vehicles. The underside of the ice is very rough, and in fact it can extend to 10 meters or sometimes 20 meters under the average ice floe depth. And here you see how algae accumulate in all of these little ridges. They form thick biomasses, and now, for the first time, when we can create maps of them, and we can figure out how much carbon is actually stored under the ice. That explains, for example, why we have seals and polar bears and polar foxes in the Arctic, also in wintertime when there's nothing else to eat. So there is quite a food web that is accommodated by these under ice algae, with also some polar cods and other crustaceans feeding on this. Now, when you try to focus away from the surface and into the water, you see it is full of particles. It almost looks a bit slimy when you look here. These are all gelatinous organisms that we observed growing at the end of the phytoplankton bloom. In fact, they eradicated all of the algae that were floating, not the ones that were hiding in the ice. And these big slime balls that you see here swimming by are lavaceans, appendicularians. It's a very strange phylum of life, one that attempted to build the first coral nerves. And, but basically they are voracious predators. They filter with their slimy houses all of the particles from the seawater, and they can entirely clear the seawater. Now imagine you would have to catch such slime balls to quantify their masses or to quantify how much they eat. It's impossible. When you tow a net, you destroy them. You have no way other than vision to quantify them. And for us, it was the first time that we could document such an abundance of life under the ice. And now we're coming back up to our beautiful Arctic landscape. And so you can probably understand by these pictures how enthusiastic, including the captain, everyone was when we had these movies shown in the ship. We could display them not only in the operating room, but also elsewhere in the cinema. And all the people gathered to watch the first images from under the ice, because it's one of these habitats that we have never seen before. And so we are just about understanding them while we're also changing them. Thank you for your attention.
Thank you, speakers. Now I'll open the floor for questions. Do we have any questions?
Mary Miller from the Exploratorium. I have two questions. You said, I'm curious about how you do navigate these vehicles without GPS, and also where did this video go? It looks just amazing. I want to see more of it.
I can probably field the first of those questions. So the vehicle relies on a suite of sensors that are used normally to navigate on the seafloor for dead reckoning. So it measures its velocity relative to the seafloor, except in this case we're measuring our velocity relative to the ice above. And of course the ice is moving and rotating, and it turns out that that particular sensor can't see that rotation. So in addition to dead reckoning on board the vehicle, we augmented that with acoustic ranging between the ship and the vehicle. And that provided a powerful constraint on where things were and allowed us to correct for the fact that we couldn't observe the rotation of the ice on the vehicle. And so, yeah. And the second part of your question, the video. Yeah, that's probably the best question for you.
We have the video archived at Woods Hole. We have about 16 hours altogether archived away, and that's one of the things people are asking, what are the results that they wanted to know 2 months ago, about 6 weeks after we got off the ship. And Antje and I are busy. That's our job for next year, we're going to be working through those videos to do the analyses, to actually start doing the quantitative scientific analyses with those things. And
yeah. So the first data show that we have really been there at one of the biggest blooms that have been observed so far. In 2012, as Chris pointed out, Kevin Arrigo has already observed one by a deeper one. But to have this bloom really in these top 2 meters of meltwater and seeing the full succession from the algae growing to all of the animals coming and eating all of that, that has been new. And so now we have to talk to the zoologist for looking up all of the jellyfish. In fact, we showed here only the larvaceans. But what we could see are these very big Arctic copepods. That was the most fascinating part for me. So when we first set up the dive and I came in the first time into the control room, I basically could see into the eye of such a thing swimming next to me, because the cameras are also enlarging things. So you can then really see how they are swimming towards you. So the copepods grew and ate the algae. Then the ctenophores, this is a special kind of jellyfish, a very pretty one that glitters in the sunlight, came and ate the copepods, and then we had these big larvaceans that eat about anything because they're so sticky that life accumulates. And so, but then in the end we had to leave. We had polar bears all the time around us, so we had also seen seals and polar bears feeding on seals, but so we can't put the food web fully together, so we don't know what eats all of the jellies to provide enough food for seals and polar bears. This is still a question to be solved.
Hi, Howard Lee, freelance. I just want to make sure I understand some of the climate change implications of what you've been saying. It seems to me that what you're saying is as the ice thins, you get a larger expanse of this algae, which presumably darkens the ice, which presumably lowers its albedo, which makes the ice thin, and so we go. Is that about right?
Yes, that's about right. So we have still to figure out how long we can get more algal growth. First, you would think more light means more algae, and so there are already people thinking about going fishing in the Arctic, because we also have this idea that cod can move up into warmer waters. But in reality, so the other limiting factor is nutrients. And because of that stratification from the meltwater, freshening the surface of the Arctic, and having no winds that mixes it as long as there is ice, we don't know where the extra nutrients should come from. So we actually cannot answer at this point. I've been to a modeling workshop in the first day of this conference. Still, we really cannot answer that question, will the productivity increase or be stable or decrease? Because to predict where the nutrients should come from with an increasing stratification is at this moment not possible. At this point, we know it's nutrient limited, so the blooms always end before the light ends in September because they have consumed all the nitrate. So if you are good about these numbers, the Arctic starts out with some 8 micromole of nitrate, and that doesn't get you very far. Through summer, you need mixing of waters. So the other big question that we need to answer is, and we have some profiles that we need to evaluate, when you have this melting, will that cause some upwelling of any kind? When you have the flows moving around, does that mix the water? So the ice algae that hang onto the ice, do they ride like on a bus and get more nutrients? All of these questions have not been solved because we had no ways of sampling at the right scale so far.
And that was an important thing we demonstrated in terms of the operation of the vehicle on this cruise, was our ability to actually collect very gentle profiles rising gently to look at those vertical distributions, and actually up to the point where we could actually land on the underside of the ice. You may have missed that, but that was the point Mike made, that not only did we have an ROV that could land on the seafloor, that as well as driving around beneath the ice, we can actually rise right up to actually resting on the ice and becoming stationary. So in the future, we're going to be able to collect the nutrient data, for example, from all these different areas, not just the temperature and salinity. We can start looking at chemical distributions. We could expand the vehicle to actually have sampling capabilities, so we can actually do a lot more. But for this first expedition, we just had to prove we could actually take the vehicle and put it in the right place to do the kinds of science we want to do in the future.
Randy Shostak, reporter with EOS. Antti, you mentioned that when you wrote your proposal, you wrote into it that a robot would exist 5 years from that point. I'm wondering if the three of you could respond to how did and how are the scientists and the engineering team working together on this to optimize the Nereid?
Well, I think it's a continual push-pull. So there's always we're on the engineering side, we're trying to push the technology and trying to anticipate to some degree what scientific needs might be, and at the same time communicate what our capabilities are to the scientific community. But in no way can we possibly imagine what people might want to do with such systems ahead of time entirely. So we build them to be flexible and well, to occupy first of all places where sort of operating modalities that aren't already currently occupied by existing systems, and secondly to be adaptable and flexible enough. For instance, having a large payload so we can adapt to different kinds of sensors and do different types of sampling and measurements.
I think an important part is a large research institution, of which WHOI is just one. It's not the only place, but it's a good example of a place where a large team of engineers, innovative engineers, and scientists work in collaboration in close proximity, which allows for those feedback loops all the time, that a first set of scientists can identify a problem, like the one I was spelling out today, and said, wouldn't it be great if there was a machine that could do something that would help advance the science, and the engineers can start building those things and say, well, here's what we could do, and then would you like to do this, would you like to do that? And historically, over my 20 years of working at this interface between science and engineering, the really coolest thing is as soon as you build something that's new, that was designed for one purpose, the first time you go out and use it, you find you generate an entirely new scientific vocabulary, and you develop a whole new range of programs that you can now go and pursue scientifically, where you could not have posed that hypothesis previously because you weren't even aware of a certain situation or a process. Mm-hmm. And I think the video we just showed you was exactly that kind of thing. I think there wasn't anybody on the ship that had predicted what we saw.
Yeah. And it needs some risk-taking as well. Of course, that is hard, huh? Because all of these things are very expensive. If you go on a mission, these days, you are not even allowed to propose a scientific mission at sea that is just for testing technology. We don't get this. You have to do hypothesis testing. You have to know exactly what your question is and what your results should be. So what I had hoped for, and it was fully satisfied, is that we did a good rigid program at depth, but we could use a lot of extra ship time for testing. And some robots robots can only be advanced in the field, so you can stay at home and try really hard in your port or in your test basin, but the situation to have ice on top and to respond to the environment, that makes the robot then evolve really fast, as it does our understanding. And well, I was very happy that the guys took the risk to come along. It was a close cut, I think, because the final pre-tests were done in the port before we steamed out. And my other point that I would like to highlight is also the need for international collaboration. So what do you do if you have one of the best icebreakers in the world, but we just simply don't have that robot technology in Germany? Should I go out, or should I wait for another 10 years till we have it? So to have to work in a world where I can call the team that is best for doing one type of technology, one type of science, and to bring them all together, you probably don't know, but there is no funding that exists that answers to that. So we have to do it by networking, by a lot of extra work, by trying to match our proposal writing. That was very difficult for this mission, and some of the funds, I think, even came from all of different bits and pieces, from even outer space research. We brought some in from astrobiology, from deep sea, from whatever, just to make it work. So that's that risk-taking that you need to realize new things.
And in addition to Antje's generous words about us taking the risk to go out, it was also really important we had somebody so enlightened as a chief scientist they would invite us and actually trust us to come up and show up in the first place.
So we have a question from the chat.
Yes, this is from Bas Den Haan, freelance, for Antje, if I'm saying it right. Sorry. I'd like to hear a little bit more about these slimy life forms. What exactly are they called in English and Latin?
Oh. So you call them lavaceans. You write this like larvae, and this is because zoologists originally thought they were larvae to a larger organism, and because they looked so funny with this little appendage, so they thought there must be something beautiful when it's grown up. But no, the adult also looks like this, just like this little slimy thing. So it's appendicularia is the Latin, and we call it lavaceans because that name sticks simply to it, that it looks a bit like a larvae swimming in a big slime housing. So these slime housings are really relevant for biological oceanography because the organisms filter a lot, and they take particles from the seawater, and eventually when they have nothing to eat, they can leave the slime house, and the slime house gets heavy and sinks to the seafloor. And we know from other areas of Earth, especially the Atlantic, that some of the biological pump removing carbon from the surface to the depth, that this is done by these organisms that can have massive swarms, but such a thick swarm as we saw in the Arctic, I've never seen before in the Atlantic. Other ones were ctenophores. So this is CTENO4, like holding the little filaments. And the other ones that we had were chetognats. Those are arrowworms, also some predators that ate the little copepods.
Laura Popek, freelance. I'm wondering what types of questions you would hope or someone would hope to answer using the ROV under a glacial tongue, if that's the ultimate goal.
Yeah, well, one of the big questions is what's happening at the grounding line of glaciers. So there are a few glaciers in the world where 20 kilometers will get you to the grounding line. So we're looking potentially at the Thwaites Glacier in particular in Antarctica. And even just seeing that environment, I think will offer a new kind of perspective because it's not really been done before. So that's not a glaciologist, so I think I'll probably leave it there.
Yeah. It's a big question in climate change. So when glaciers start sliding, they transport, they eventually break off, and they transport large amounts then of ice that melts eventually, and that has a big effect in the end on sea level, of course. And exactly that process, when they start losing grip and when they start sliding, as they did now big time in Antarctica, this is one of the key questions that needs to be answered to us understand the future of sea level and the future of the cryosphere.
Other questions? Okay, we have another from the chat.
Yeah, this is from Carrie Sheridan at AFP. I was wondering if the results are being published in a scientific journal or if there are plans to do so.
There are definitely plans to do so. We actually have some first presentations this afternoon, which is our first reports in 2 sessions of the Biogeosciences section. So that's the first thing. The abstracts of those are the first things that have come out from this. And I'm actually going on sabbatical to Germany straight after the new year, so we can get stuck into the data and we can start working that up.
Yeah.
I might add that we've actually done a publication in the robotics literature as well, since this was a fairly ambitious deployment for an undersea robot. So we're waiting to hear back on that. But got lots of engineering data to go through as well.
Do we have any other questions here in the room? Any others from the chat? Okay, I think that wraps it up. Thank you very much, speakers, and thanks everyone for being here. Our next press conference will be at 9 o'clock, and that one's on California's epic drought as viewed from space.